We propose HANDLOOM 3.0, a framework for robotic multi-cable tracing in cluttered environments. HANDLOOM 3.0 implements a novel algorithm for integrating multiple deformable cable state estimates for divergence point detection. In this video, we demonstrate a Tier 3 run of a successful cable trace. We begin with 3 cables scattered in the workspace and 3 objects. Note that one object is not actually occluding the cables. Given a top-down 2D raw RGB image from the Brio camera, we run our endpoint detector model. We then run DEDIC to segment the objects and retrieve their masks. The algorithm finds an initial trace starting from each of the 6 endpoints. If the tracer intersects with the DEDIC mask along its path, it terminates. The robot will now declutter only the objects that are interfering with the trace. In this example, the white bag furthest from the robot does not occlude the scene, and therefore will not be decluttered.
We then perform divergence logic on the scene. We assess the correctness of the trace using reciprocal consistency, that is, whether the forward and backward traces from a given cable's endpoints are identical. For example, we would expect the trace mask from A to B to be identical to the trace mask from B to A. If these 2 traces are different, there exists a point of uncertainty where the 2 traces diverge. We label this point of uncertainty, where the cables transition from overlapping to non-overlapping, as a divergence point. Through this novel bi-directional tracing approach, we determine the exact point where an interactive perception primitive is required. We then use the local cable density to classify the divergence point as either a tangential crossing or a high-density cluster. The density is calculated using the percentage of pixels occupied by cables within a fixed radius. If this density exceeds a certain threshold, such as in this example, we perform a cluster dilation rather than a divergence push. To disambiguate the cluster, we find all open regions near the divergence point and select the region with sufficient area for gripper insertion. We then insert the closed gripper into the region, open the gripper, and spin.
The pipeline continues by retracing from all endpoints and performing object detection. Note that the algorithm runs object detection throughout pipeline execution, not just at the start, enabling dynamic decluttering based on the updated state. In this example, there are no interfering objects, but a new divergence point is detected. This iteration, the local cable density is below the threshold, so we perform a divergence push to separate the tangential crossing. We calculate the tangential lines to each cable, shown in blue, and bisect it to find a divergence push angle, shown in red. We then plan the move, shown with the red vector. After the second trace, there are no more divergence points, the forward and backwards traces of each endpoint match, and the trace completes.